Hey everyone, I am here today to answer the question of why does the angle change like it does to get the maximum range when launched at a different height than the landing height. Alright, so why does the angle change like it does so that we can get the maximum horizontal distance when an object or a projectile is launched at one height and land at a different height? Alright, so to start with, I thought that I would basically show a drawing of things, and imagine, if you will, what's going on here. We have a level surface with a projectile being launched at, we'll say the 45-degree angle. All right, for this case, we get a maximum range out of that. All right. If an object were to land higher than what it was launched from, all right, so it's launched at same 45-degree angle, so it goes, and then hey, look, there's actually a second here that didn't actually happen. The ball was no longer in motion because it actually hit the ground between this second and that second. All right, so here the ball basically hits the ground, and since the ball hits the ground sooner than what it did here at the 45-degree angle, then that is less time that the projectile had to move horizontally. All right, so less time, this projectile had less time to move horizontally than this projectile did on a level surface because of the height change. All right. Going further, this one isn't as awesome, but it'll still work. We have our projectile is launched, and then it lands lower than what it started from. All right, and as we talked about in class, how when an object is launched from a greater height, then you need an angle less than 45 degrees in order to produce the maximum greatest distance. All right, horizontal distance. Whereas here, you needed an angle greater than 45 degrees in order to get the greatest distance. And the question is, why is that? All right, going back to our original question of why is that? And so, as I started to allude to, it has to do a little bit with time. All right, because since we have this higher landing zone, it's less time to go horizontally. Here we have a landing zone that's lower than, so theoretically we should have even more time for it to go horizontally, but yet there's a catch to that. All right, there's a catch to that, in that when we think about 45-degree angle being awesome at a level surface, here we actually need a lower angle in order to get a maximum range. And here's part of the reason. All right, this is the conceptual idea behind it, and then I'll go into a little bit of something here in a minute. But the concept is that the projectiles have both horizontal and vertical vectors, right? We have horizontal and vertical velocities, all right? Along this entire thing, you can basically draw your different vectors, all right? Your horizontal, of course, is going to stay the same the entire time, right? But the time in the air is what's important here, because if we can get the object to stay in the air a longer time, then that means that the object or the projectile will go horizontally for a longer period of time. All right, so we don't necessarily need a 45-degree angle anymore. We just need an angle that is less than 45. So, if you think about your protractor and how that looks, so less than 45 degrees, then that'll keep the ball going. Yes, it's a lower angle, all right, but it doesn't spend time having to go up. It can just keep going horizontally, because guess what? Now we're at a lower landing zone, all right? So we're not worried about the ball dropping as much as it was going to, all right? Because now we have even more space for it to fall, all right? So since we have this more space for it to fall, it can continue to go horizontally longer, all right? So we don't need that 45-degree angle anymore. All we need is an angle just to get us, to keep us going in a prime location. We need that angle to just barely, skim the surface a little bit, depending on how high this actually is. You can just get it going, and then gravity will eventually bring it down to another prime, to your maximum range. All right. I hope that answers it conceptually, that it has to do with balancing between your vertical and your horizontal vectors. All right. And also the idea of time. All right. The idea of time that the projectile would be going horizontally. All right. Because if it's not moving up and down, then that means it's also not moving, it's not moving horizontally either. All right. So that's the concept. Now there is another way to think about it besides this, and that's going back to our kinematic equations. All right, going back to our kinematic equations, and thinking about them, especially the equations 3, 4, and 5. All right, I'm going to focus more on equations 3 and 5, but the fourth one is still very important in all of this. All right, so starting with the third one, all right, we have our final y velocity equals our initial y velocity plus our acceleration in the y direction, which is gravity, all right, times time, all right, remembering the fact that time is the connecting piece between the horizontal and the vertical, all right, so that's the time piece is the connecting tissue, all right, so if we connect that, and time is connected with our final velocity, all right? Then going down to the fifth equation, all right, our final velocity equals, or our final velocity in the y direction squared equals our initial velocity in the y direction squared, plus 2 times our acceleration in the y direction, which is once again gravity. Multiply that times your change in y position, so you can say either your final y minus your initial y, or you could just say delta y, however you think about it. All right, it's really all the same. But notice that now, instead of having time being a dependent factor on your final velocity in the y direction, now we have our change in y is going to be a dependent factor in figuring out what our final velocity is. All right, so that's another reason why, going back to the picture here, that if we have a higher final than our initial, all right, so higher final than our initial, then that's going to have an effect here that it's going to actually decrease our final velocity, all right? Whereas if we were to have a lower final, so a lower final than our initial, then we're going to have a higher final velocity. Because yes, if you think about, well, you're subtracting this, so that means that could be a negative number, or it could be 0, and so yf would have to be less than 0, and that would actually work out, because remember, your acceleration is negative, so it's negative 9.8 multiplied times a negative y direction here. All right, so that would actually increase your y velocity, which if you increase your y velocity, you're essentially having an increase in time as well, because in both cases your acceleration is going to be the same. All right, let me know if that answers your question. If not, I can do another video, come at it a different way, and send me a comment, send me an email, give me a thumbs up if it works for you. All right, let me know how it works, and we'll see you tomorrow.